Ready to roll? Okay. Well, good afternoon or good morning, as the case may be, to everybody. My name is Peter Srajer. I'm with ProStar Geomatics, and in this webinar here, it's the 15th webinar from CUIIC, Canadian Underground Infrastructure Academy. We are pleased to have everybody joining us here. Today we have a very exciting webinar put on by a group of great people who are from all over the world trying to come here and tell us their amazing award-winning custom-built drones for surveying buried pipelines and confined spaces. Thank you very much for joining us. These webinars are organized by the Canadian Underground Infrastructure Innovation Centre, which is a kind of a conglomeration of groups, including the University of Alberta and Benjamin Media. CUIIC Academy offers several courses, classes, webinars, and events in a kind of a understanding or help understand the underground infrastructure educational opportunities across Canada. And welcome and thank you to everybody on this. There we go. Sorry. We have a series of CUIIC Academy Webinar Series free to everybody who wants to join. They cover a wide variety of pressing topics, mainly related to the underground infrastructure sector. We've had several incredible speakers, including industry-leading professionals, and who provide a monthly free educational workshop or webinar to the public. We'll have a question and answer period as well afterwards. So if you're looking to enhance your knowledge in this area, please join us every Thursday of the month, 1 p.m. Eastern Time. And if you wish, there's a full schedule of events at academy.cuiic.ca. Just to give a shout out to the upcoming webinars before we head on to this one. The next one, April 18th, is on high accuracy data collection to support subsurface utility engineering and locate sketching. And on May 16th, the Diagnose, Advise, Treat process to rehabilitate manholes and underground assets. Greatly appreciative to have you join us for those ones as well. As well, we have a CUIIC Academy, more day-long or several day-long events held at in-person locations in April 24th and 25th at the Calgary TELUS Convention Center. We have the CUIIC Advanced HDD School. Want to go into the full details here, as you can go onto our website and see this. And as well, in May 30th, 2024, the CUIIC Geotechnical Risks and Consideration for Underground Construction Workshop. Both very valuable and exceptionally well thought out events. So please go to our website and take a look at that. Before we head on to our presenters here, I'd like to a sincere thank you to Westlake Pipe and Fittings for being our 2024 webinar series sponsor. Very much. Right. Now on to our presentation here. We have a number of distinguished guests here who will be speaking on this. I'm going to kind of do a short introduction to each of these individuals. And again, thank you as well for all of them coming to do this. Thomas Philbin is the operations manager at Environmental Techniques. Ross Grant, project manager for Caledonia Water Alliance. Jack Hutton, director of Good Friday Robotics. George McClugan, contracts director for Dawson Wam. Mark Mitchell, the head of capital delivery for Northern Ireland Water. Ian Jones, is a risk and life cycle planning manager over at Scottish Water. And I will be handing this over shortly to Shauna Herron, who is the managing director of Environmental Techniques. Shauna, the webinar is yours.
Thank you, Peter. Welcome here from Scotland, and thank you all for joining us. Our first speaker today is actually Ian Jones, and we're going to play a short video about Scottish Water. So if we can play that video now, I'm going to ask Ian Jones to come up and present his slides. Thank you.
Scotland is blessed with natural beauty. Unspoiled wilderness, deep lochs, ancient peatlands. Our rugged coastline spans around 12,000 miles, from wind-whipped beach to surging shore to far-flung fishing ground. For millennia, folk have lived in this landscape and relied on its natural gifts. In our modern world, we still depend on nature, and water is perhaps the most priceless resource on the planet. In Scotland, we may feel like we get a lot of rain, and due to climate change, it now rains 13% more than it did 100 years ago. But today's rainfall comes in surges, so it's harder than ever to manage Scotland's water. Heavier rain washes peat off the hills, organic matter can make some water discoloured, and warmer water takes more effort, science and money to make safe and pure. To keep our water the way we like it, cool, fresh, clear, straight from the tap. So let's spare a thought for what it takes to pipe Scotland's water to your home while you run a tap, brush your teeth, take a shower, wash clothes, make soup, enjoy a cuppa, water your plants or flush the loo. Scottish Water produces 1.5 billion litres a day, every day. The average person in Scotland uses about 180 litres of water a day, far more than people in England and elsewhere. And our infrastructure was never designed to cope with this demand, or the pressure of population shift, or the extremes of climate change. Scottish Water invests over £800 million a year in infrastructure to keep our water system running. We also look after more than 60,000 miles of pipes, over 2,000 treatment works, and around 300 reservoirs, all to ensure that everyone has access to beautiful, affordable water, but also to ensure that wastewater is thoroughly treated, recovering resources as it's safely returned to the environment. It takes more than 4,500 people to provide Scotland with quality water, and wastewater services we've all come to know and expect. Engineers, scientists, customer service representatives, computer technicians, security analysts, the maintenance teams you'll see out and about in our distinctive vans, even water tasters. On average, our expert water samplers test the water we supply to your taps every 2 minutes to ensure its purity. The water we all take for granted is a massive undertaking. Scottish Water is publicly owned, and every penny we make is reinvested for public good. In return, all we ask is that all of us respect this precious resource, to value this astonishing stuff which literally falls out of the sky. Because water is vital to the health, well-being and prosperity of the nation to help support a flourishing Scotland. Scottish Water. Cool, fresh, clear, and only available right here.
We have seen an increase in awareness not only in Scotland but also further afield as to just how important water is. We know there are some real challenges to address with no single quick or easy fix. The combined pressures of climate change, ageing assets, for instance, much of Scottish Water's sewer network dates back more than 160 years to Victorian times and was simply not designed for today's weather, was population change and the welcome increased public awareness of the value of our natural environment means that we need to transform how we work with respect to delivering service for our customers. For Scottish Water, this means being bolder, more innovative, more collaborative, as we work differently with our partners and associated supply chain, but also how we engage with our customers to become active participants in the changes that we need to achieve to benefit us as a society, and also make sure our customers are not simply passive recipients of a service. Our strategic plan, Our Future Together, sets out 3 ambitions: to deliver service excellence, deliver great value and financial sustainability, and go beyond net zero emissions. Scottish Water has an ambition to be a net zero organisation by 2040, and this is something we don't take lightly, and in fact is at the centre of all our ongoing plans for transformation. Our stakeholders expect us to continually develop our knowledge and capability to drive towards our ambitions, and therefore we created a set of innovation route maps that align to meeting those challenges. In the case of eliminating greenhouse gas emissions, we have 2 outcomes that we assess innovation against, such as zero process emissions and where practical, all construction activities are zero or low carbon. Our strategies for service support our long-term water sector vision and provide our key stakeholders with the evidence that they require with regards to financial costs associated with this service provision. We need to secure the ongoing investment needed to deliver net zero by upgrading our assets to adapt to climate change impacts that we are already seeing in relation to both drought and flood risk. This must also be done within a framework that supports a circular economy mindset, such that we can ensure alignment with the Scottish Government's Circular Economy Bill. Creating a circular economy means making changes to the way we produce and consume things so that we can reduce, reuse and recycle more of the materials and products that we use in our everyday lives. The aim is to prevent waste, which will reduce environmental pollution, such as discarded plastic in our rivers and our oceans. As we embrace concepts such as the circular economy, we need to provide a simplified view with regards to translating our route map into a prioritised innovation programme. This prioritisation requires us to take account of strategic need, and as such has driven the requirements to innovate in some of our priority investment areas, such as critical infrastructure. It needs to consider how we scale up demonstrators in a manner that provides certainty of benefit, not only for Scottish Water, but also for our partners, as we all must consider the capacity for our respective businesses to adopt the innovation and understand the potential impact, both positive and negative, on resource availability, people, finance, and a whole lot more. As a public utility, Scottish Water are funded by customer charges and borrowing, and therefore it's critical that our customers understand and find a synergy and an alignment with the outcomes of our strategic plan. Perhaps the biggest challenge that everyone on this webinar will ultimately face will be related to how we all work collaboratively together to ensure that as a wider society, we maximise the value of all our assets, intervening as and when appropriate to ensure that the service levels to our respective customers are not compromised. It's my belief that over time in Scotland, our principal regulator, which is currently SEPA, will inevitably be taken over, and it will be our customer base who will be regulating on behalf, because they'll have a greater and a more informed opinion with regards to the resilience and the performance of our assets, as they will have a lot more access to use our own data and our own information to do that. Key to the delivery of our projects are the skills, capacity and the experience of our people and our delivery partners. We have around 400 supply chain partners, with 90% of our procurement staying in the country. Last year we spent £1 billion, up from £864 million the previous year. The key challenge that Scottish Water set for this team was quite simple. How can we carry out significantly more programmed inspections of our critical wastewater infrastructure, which up until now had been nigh on impossible to survey, and do it in a manner that drove a 15 to 20% saving on the overall programme value when comparing it to our investment between 2015 and 2021. And if that wasn't hard enough, we then followed up with and how can we develop follow-on programmes of critical maintenance that comply with our asset class management approaches, such that we start to reduce the amount of work involved in defining the follow-on remedial interventions. And finally, how can we ensure that there is a consistency in our decision-making such that we intervene prior to any significant failure in our service?
Thank you, Ian. I'm now going to ask Ross Grant to come up and speak. Thank you.
Hi there, thanks Ian. So I'm Ross Grant, I'm a project manager for Caledonia Water Alliance. As Ian's kind of pointed out in the slides, the challenge was set out by Scottish Water to come up with an innovative solution that could help, transform the wastewater services and how they work. So as part of the search for innovation, we had approached environmental techniques in the first instance to see what could be done. We had various sort of large schemes of survey works going on in both Edinburgh and Glasgow. So that seemed like a good place to start. We'd agreed to develop something collaboratively that we could then, present back to Scottish Water. So there were a few sessions, plenty of ideas were put forward in terms of, what could be innovative. We looked at things like reinstatement, looking at low carbon cost materials, things like that. We got to the point where we presented some of these back to Scottish Water and, quickly met with, appreciate the thought and effort, but not quite what they were looking for, which, at the time, bit sort of, demoralising, but it kind of went, right, okay, let's kind of get back to almost the sort of basics and what can we do and what can we provide to, something that would be sort of truly innovative, that would actually help. So going on the back of the kind rejections, there was a positive and realistic opportunity within the survey area that came to light. As Ian has kind of mentioned, there's a lot of existing assets, a lot of critical assets that remained unsurveyed, which again I'll cover in some of the following slides. We looked at the issues related to surveying these sewers, what could be done to overcome these. We looked at, the idea, this is where the idea of the drone survey came about. Well, it's not a new concept, it's just something that has never really worked in the past or worked to, what we need or what we needed from it. So through the sort of collaborative approach, this is where, Good Friday Robotics come into the frame as well. As part of that collaboration, the trials were sort of started in February 22. There was, sort of incredible success over those 2 years, which again will be covered in the presentation. And to be honest, it's something that I've personally been very, very impressed with. So as I mentioned previously, there were many sewers that remain unsurveyed, and this is sort of globally. This is, again, more the sort of critical assets, which again, if there's any issues with these assets, it can lead to bigger problems, have a huge impact on surrounding areas and have major sort of significant customer impacts, which, is something that we want to avoid. There's various reasons why the assets remain unsurveyed, as sort of noted there. You've got challenges including difficult areas to access, high flows, debris and hazardous gases. The sort of more traditional survey techniques would mean exposing people to these environments and pose a significant health and safety risk. And surely this is, one thing that we want to try and eliminate. Given that confined space incidents account for 10% of all work-related fatalities in the UK, it's, it sits top of the list in terms of our health and safety risk. Following on from the last slide, the traditional survey methods, such as the sort of crawler float systems that we would normally use to survey the sewers, would have difficulty in some of the sort of more obscure sewer networks. These networks were, constructed, well over 100 years ago. So the methods to survey are incredibly difficult. So a lot of these would require sort of man-entry, things like that, which again has its own sort of hazards. You've got the slip, trip risk, again the hazardous gases, risk of drowning, and these difficult rescue procedures. A lot of these sewers are in difficult areas. They will, it's the depth as well that some of these sewers are at. It just creates problems that you want to try and eliminate. So what this does is it leaves many of these critical assets at risk, as no one knows the current condition of them. As to be expected with these confined spaces, there's a good chance of encountering gas within the networks. And as one example that we're currently doing, we have got a large survey programme of works up in Aberdeen. There is a sort of mystery unidentified gas that sort of resides up in that area. So this was one sort of part of it that we want to try and eliminate, and the drone is, ideal for that. So yeah, that's pretty much that one there, and I'll pass on to Thomas.
Thanks, Ross. So yeah, I suppose we've heard about the challenges and the questions asked by Scottish Water and then CWA, and also looking at the solution. So this is where it starts to come into the innovation itself. This slide here, you can see the amount of operatives involved in carrying out what Ross described there as a man entry or a person entry into a sewer to carry out a survey. Up to 13 operatives on site, fairly extensive traffic management, and the risks that go with that, the disruption that go with that, the excessive use of carbon, if you like, that goes with that, and the time on site. So what we have done, and you'll hear a lot more about the actual innovation itself shortly, is introduce the drone survey and reduce what you can see here to what you can now see on this slide. So an extreme reduction from 13 down to 2 operatives on site, down to 1 access point or exit point, and no person entry into the sewer. So we've eliminated those hazards that Ross previously described, eliminated that issue that we could come up against in carrying these surveys. And ultimately, what we're doing is solving that original problem. We're now surveying these things, these sewers, these assets that were previously unsurveyed. So the solution itself, as we say, the drone engineered solution. What do we find from that? We're finding that we have got increased operator safety, as we discussed. We've got increased productivity. We're able to carry out more drone surveys in a shorter space of time than we previously were able to. Increased quality assurance and accuracy. We'll talk about that shortly. The reduced carbon footprint that I mentioned. We are reducing the number of vans on site. We're reducing the number of people needed to be on site, and we're reducing the disruption to residents, etc. And then there's ongoing initiatives. We can also have a review of where we're going with this as well. So on the drone itself, we have a high-level view of what we intended to do and where we were this time, probably June 2022, and we'll lead on to some of the projects that we actually implemented this on. So the drones are equipped with, or the drones were equipped with 4 LiDAR sensors and multiple camera systems. The LiDAR there is to stabilise the drone, and also we found through discussions with Scottish Water, with that feedback and that collaboration, that we were able to use the LiDAR information for future use. We could talk about that later on in this webinar. At this time, we're now plus or minus 3mm accuracy on the drone output. Again, we can talk about that. You can see on this slide here, this is an excerpt of a project that will go into a bit more depth from in Northern Ireland with Mark and Gerard. It's a 3D scan carried out by the drone. We can measure diameters, we can measure diameter changes, we can measure the lengths involved, any deformation, any angle changes, line deviations, and size of defects. All of this comes through the survey, comes through the LiDAR point cloud data, and the analysis that then goes on the back end of that. So it's given us far more information than we ever had before. And again, more detail as we go through this presentation. The maiden project that we implemented this on was in June 2022, and it was on Bath Street in Glasgow, named Project Elida. On this slide here, there's a short video. I'll talk about it, I'll play the video, and then we carry on with the presentation. On the left-hand side, you can see the point cloud data. On the top right-hand side, you can see the video output. And what you will see as the drone flies through the asset is where it passes beyond a traditional crawler survey limit, which is a theme that you'll see later on in the presentation. So if we can just press play on that now, if that's okay. Thank you. So what that output showed us from the original GIS input, if you like, was this is the original route, the original location plan shown in red, and then the updated LiDAR plan shown with the point cloud data there in the green on the left-hand side. Huge difference in what we expected, huge difference in the information that we had, and it now allows our client ultimately to see exactly what is happening with their asset, where it is, and any issues that are associated with it. So you would have seen the defects that we've picked up on. We now have a second challenge, which is to now remediate and rehab that asset, but that's for another webinar. So what I'll do now is pass on to Mark Mitchell from Northern Ireland Water, who'll give you an overview of how we took this investigative innovation and pulled it into an actual repair solution. Thanks.
Thanks, Thomas. Hi, everyone. Afternoon. As Thomas said, I'm going to chat a wee bit about Queensbridge siphons, which are under the River Lagan in Belfast and have been since 1910. These were installed, they're approximately 4 foot diameter and 30 foot deep, or 1143 millimeter and 9 meters deep. You can see from the slide the location, and if this was a shot that was taken back when these were being installed, just underneath the N and the S on the of Queen's Bridge siphons on the top, there's a building there, and that's the Titanic Centre, and that's where the Titanic was sitting on the dry dock as these were being built. So we're still using these. Very sad story of the Titanic, but and also the Olympic was there at the same time. But anyway, back about the turn of the century, we realised the siphons were not performing as they should be, and we did a bit of investigation. We knew the siphons were the north siphon in particular had a problem, and it was blocked, and we weren't getting the flow through at all. So as these two siphons take approximately 40,000 PE across the River Lagan to the sort of north and west side of the river to go to the treatment works, we knew something had to be done. What we did know was that in the we had good Victorian era drawings of the siphons. We had good sections. We had a cofferdam plan of how they'd been installed. So we thought, as per usual, natural thing here is let's see if we can have a look at them. But push comes to shove, we'll employ one of our tier one contractors who will cofferdam this and replace the siphons. Dig down, excavate it out, and replace them in conventional manner. We did a bit of investigation and a bit of a look, and we could see siphons were in a terrible state internally, and so this refurbishment was going to cost us around about £20 million. That's 32 million Canadian dollars at the time of going to press. Dear knows what it is now, but with our wonderful political system, we have prime ministers jumping in and out of bed. But anyway, what we have here is we have a solution that was going to cost me 20 million. I employed Dawson Wham to have a look at it, and I'm going to pass over to Jared, who's going to give you a bit of an insight into how Dawson Wham approached solving the problem.
Thank you, Mark. Just to put the scheme in context, we were awarded this contract back in early 2022, and we appointed Environmental Techniques Aegion as our specialist subcontractor. CAPP lining was proposed as the preferred repair solution in lieu of the traditional heavy civils replacement. One thing that Mark alluded to, there were significant problems in the north siphon, and as you can see here from the diagram on the scheme, we actually identified that there was actually a diameter change in the north siphon, We then found out that this was as a result that the North Siphon was actually damaged during extensive bombing in the city during World War II, and it was repaired thereafter. So this proved a significant challenge for us because, you know, we needed to measure this siphon accurately to basically make the liner to fit. So what we did was we used, and Thomas had alluded to some of the footage earlier, we used the drone technology to actually survey both siphons, but in particular we used it to identify the North Siphon and this change in diameter and to measure it accurately. So now I'm just going to show you a short video of that North Siphon. So you could play the video, please. So as you can see, with the level of detail that the drone was able to give us with the then 4K imagery, which is now, I believe, up to 12K, we were able to clearly identify that not alone there was a significant diameter change, but you can see the clear transition between the old cast iron to the repaired brick solution, and then that ultimately identified what the problem was with the choke in the northern siphon. So here you can see now, just similar to what Thomas showed earlier in his scheme, you can see here this been overlaid. So we have the original route, and you know, we had just assumed that there's about 143 meters of distance between the chambers to the east and the west of the river between the siphons. We had assumed that it was just a lovely straight line between each, but which is identified as a red line. And then when you actually use the 3D imagery we received from the drone, you could actually see the green line, which is overlay, which shows that it's far from that. Why is that important? Well, now at least the client has a very accurate position of where their asset actually is. And furthermore, if we were using the traditional open cut methods and going in to put in a cofferdam, lo and behold, if we assumed it was in a straight line, we probably would have ended up hitting some of our temporary work sheet piles right down through it, which would have caused even more problems. So this is the output from the LiDAR 3D imagery. So you can clearly see here that not alone the change in diameter of the siphon, but as well the change in the verticality of it. So you can see here over a 15.9 meter section, which showed in the video earlier, you can see the diameter changes from 845 up to from 1145 down to 870 and back up again. So this was really a digital twin of what was actually in the ground and allowed us to able to go and manufacture the CIPP liner accurately. Here are some images of the installation of this liner, which happened in late spring, early summer 2022 of Environmental Techniques Aegion actually on site. Just to put the thing into context, the liner was manufactured and wetted off-site in Europe and then transported to site via refrigerated container. The liner itself, as you can see, there's been installed by a crane. It was in the region of 18 tons each liner, so significant weight and significantly logistical problem to get it actually down into the pipe itself. And the wall thickness as this was in the region of 19 millimeters. And I have to say that everything went really smoothly on site and was installed very successfully. So much so here you can see just the transition where we had the change in pipe diameter in the north siphon on the small inset on the left, and there is the transition of the finished product, which is pretty much seamless. I think you will all agree. So absolutely real success. And then just finally, just on the drone and the program improvements today, initially we were expecting, a 32-week delivery of this project, but by utilizing the drone technology, we were able to deliver the scheme about 8 weeks quicker. Why was that? Well, ultimately, if we were using the traditional means, like the track unit to measure and survey the actual siphons themselves to measure for the liner, we would have had to clean out the siphons, give them a quick clean, didn't have to do it extensively, just enough room to get it down. And then with the digital twin, we were able to be manufacturing the actual liner while we were actually then extensively cleaning out the siphon for its arrival on site. So all in all, that led to about an 8-week saving by the use of the drone technology.
Thank you, Jared. Yeah, I suppose one of the things we haven't mentioned, and this was a major saving, was the significantly reducing the carbon footprint. Really, we set off on this journey to increase the safety of our operatives, was to reduce the number of people we were putting into a confined space. But as a byproduct of the LiDAR and the enhanced CCTV footage of the sewers, we've really improved the accuracy of the surveys. Another thing that Thomas mentioned earlier was about the reduction of the amount of traffic management to enable the surveys to be undertaken. We reduced the time taken. One of the other presenters spoke about that as well. So all in all, huge reduction in carbon footprint. And that really is aligned very much with Northern Ireland Water and Scottish Water's net carbon zero aims. So really now what I'd like to do is pass over to our last speaker today, Jack Hutton, who's going to just talk a little bit more detail about what this adapted drone technology can do. I'll pass you over to Jack.
Good afternoon, everyone. So I'm here to represent Good Friday Robotics, and we are a team of engineers, and basically we specialize in the solving of complicated problems with flying machines. And we operate and manufacture the drones that go through and do these surveys. But we get the credit for making the drone. But actually, I wanted to put this picture up just to kind of highlight the collaborative approach that we've taken for this whole project. So it's not just Good Friday that makes the drone. Basically, how we have taken on this challenge is it's an iterative approach that we've taken on. 2 years ago, we were asked, is it possible to actually put a drone in a sewer? To which we were like, we are not sure, we'll have to go try it. And after initial trials, it actually worked. But of course, back then, we were only able to get about 20 meters in a very, very large diameter sewer. So we went back, got feedback from Environmental Techniques. They gave us a sort of long list of requests. And through that feedback loop, we then went off and made another aircraft, changed a little bit of it. And then more and more people started getting involved in the project, like Northern Irish Water, Dawson WAM, CWA, Scottish Water. And through this, we had the perfect machine to give us the feedback necessary for us to design an aircraft that's incredibly robust and is capable of doing these incredibly complex surveys and providing outputs that are actually usable in the real world. So this is our drone that we use. This is called Thronos. And Thronos is an ultra long range confined space drone. So we can get about 400 or 500 meters from a survey from a single access point. And to actually show you on how fast the design and iteration is moving on this, it currently states that it is a 250 mil sphere, where it is not a 250 mil sphere, it is a 210 mil sphere now. For the safety side of things, we've designed all parts of this drone to be compliant with the ATEX Zone 1. So everything in that can go into the environment that sewers operate in. Secure as well, so we know that we use these within government assets, and within government assets there is lots and lots of regulations on what type of radio transmissions and what type of video transmission you can use. So we have a Blue UAS certified radio transmission, and also I will talk a little bit about our new mesh networking after this. And the development of the project as time went on, initially we had a very low resolution camera on the initial drones, and then as we sort of flew a couple of these, we put 4K on, and that was fantastic because you could see the grout and the spiders in the sewers. And now actually moving on from this, we have a full 360 video on our up and coming drones, as well as we were flying these things as we attempted smaller and smaller diameters. Whenever you fly a drone in a small diameter tunnel, you start to get very strange aerodynamic effects, as essentially you have high and low pressures and moving about air that means that the pilot cannot react as fast as the drone will actually react to the changing airflows. So we needed to put in a number of different autonomous systems to allow us to operate in these ultra confined spaces. One of these was LiDAR, and that was just to help us stabilize the drone in the middle of the tunnel. However, it was very quickly pointed out that since we were LiDAR scanning the whole thing, we may as well actually use that as an output. So I'm just going to go to the next slide here. And this is just to show you sort of a basic example of what our LiDAR is capable of capturing. This is a 30-second flight just around our warehouse. And if we could just play that video there. This is not a image, by the way. This is a 3D model. So if we could just play this. So I'm sure you'll be able to see from the earlier slides of us using drones in earlier projects to what we're able to achieve now. There has been leaps and bounds in the development of our LiDAR, and you can see just how dense those point clouds are, as well as how accurate we can actually get this scan from flying. But that's obviously in our warehouse. It's not much good flying around in our warehouse. This is still in processing, as we literally just did this flight, but this is the Belfast tunnel. We just completed that flight last week. And this is what we are currently processing as an output. And obviously you can take these models, and each of these will have a GPS tag associated with it, so you'll know exactly how deep under the ground it is, as well as where exactly it is if there needs to be remediation work, and the chainage of any defects or anything that is identified. The full 3D model allows design teams to be able to go in and accurately plan out remediation work to really help in the design stages of this, because really all we're doing at the end of the day is going down to take a look and take as many measurements as we possibly can. But thank you very much for listening. I'm going to hand back to Shauna now, and thank you.
Thank you. Thank you, Jack. And now I'm going to ask our moderator, Peter, just to start off with the questions. I've actually got a very good question that's just come in here, maybe to start off, Peter. And it's, what is the difference? I'm just going to change the view slightly so that we can see our panel here, our panel of speakers. If you can just bear with me. Okay, so the question is, what is the difference from the original idea and the new innovation along the project? And I think that would be a question for Mark about the lag and siphons.
So the original idea for lag and siphons would have been to coffer dam across the river in sections and open cut and relay the siphons at enormous, not only financial but environmental cost. And they made, as Jared alluded to, because we thought the siphons went straight across the river, there could have been an even bigger environmental disaster, because he probably would have sunk his sheet pipes down through the middle of the pipe. And the other thing for me, the really interesting thing was these were steel siphon pipes. And as we can see, because all the steel in Belfast, or iron in Belfast, had disappeared during the Second World War, it was away being turned into tanks and planes and things like that. They carried out the repair in brick, which just a little interesting fact. But the difference was that because of the drone survey, the accuracy of the drone survey, we were able to have a seamless repair and completion of the rehabilitation of the siphons done ahead of programme at a fifth of the cost, with minimal environmental damage and minimal environmental impact. So, and customer and consumer impact. Can you 24-week time frame as opposed to what probably would have been 2 years, 18 months if it was open cut in the middle of the city on a beside one of the main bridges in from the southeast to the city centre. So it made a big difference to our customer impact at the time.
Thank you, Mark. Is there a question about diameter there, Peter? Do you want to look at that?
Yeah, certainly. Just as well, for those of you on the webinar, please feel free to ask any questions on there. There is a questions box that you'll see there on your screen. Please just feel free to go in there and type in your questions. And in the meantime, I will moderate some of the other questions that are coming in. Thank you very much. I guess, first one here. What is the minimum and maximum pipe size that can be surveyed by the drone?
So currently with the latest and greatest one that we have made, the minimum and still obviously, basically the difficulty with surveying smaller and smaller diameters is you have to fly slower and slower in order to get a good survey, as you're not able to go full speed in a 700, as the walls will be flying by so fast that the motion blur means that you won't be able to see anything anyway. But the smallest diameter that we can get down to now is a 600 mil. However, that is very slow and needs to be dry at the bottom. Ideally, a 700, 800 gives a comfortable output for the drone to get a good survey.
Very cool. All right. Imagine that speed. It's hard to control that thing as well. So interesting. That's an interesting question of how accurate is the GPS. I imagine you also have an IMU on board once it's in the pipe.
Yeah. So the GPS on, basically we fuse a number of different models and points together to allow us to get the GPS underneath the ground. Because obviously once we fly in a tunnel, there's no chance that we're going to be getting any sort of RTK satellites or any GNSS satellites like that. That's not possible in a tunnel. So we fuse a number of different models together, and depending on the length of the survey, the accuracy at the end of a 100-meter, 200-meter survey, the drone is inclined to drift whenever it's that long. However, if we can lock 3 points in, so basically a couple points at the start with a GPS tag, and then if we're flying to a manhole, the GPS of that manhole at the end, we are able to get incredible accuracy the entire way, as it really doesn't drift laterally thanks to our IMU. It only drifts in its compass bearing. And if we're able to get a compass bearing, or essentially a point at the end, the amount of drift that is encountered in the tunnel is very minimal.
Cool. That makes sense. Thank you very much. Interesting question here on the actual engineering of the liner. Did you dry up completely the siphon before install the bespoke liner?
Any one of us probably can answer that. No, we never had to. So that was one of the savings that Gerard was talking about. We were able to transfer some of the flows into the other siphon, also carry out the survey first, then do the full cleaning, and then procure the liner in that sort of cleaning phase, the extensive cleaning phase. So that's where we achieved a lot of the savings. We were able to pull out most of the water, I would say, in the lower half, pretty much all of the water from the siphon from the lower section, to allow us to carry out the lining from the lining perspective. It was a bit of a challenge, and it took time, but that was time that we had because we were already procuring the liner.
Cool, interesting. All right.
I think the point is there were two parallel siphons. So you could divert the flow, because part of the work that Derek did was install penstocks at either side to be able to isolate each siphon. So you were able to divert flow down one siphon or the other, whilst one was being lined, the other wasn't used.
Mm-hmm. Cool. Well, thank you very much. Okay, that's an interesting question. How did Thronos survive major water ingress from above? Did they fly through it? Did they drown it?
Thronos is able to survive at least a good bit of splashing, as all components in the newest version are completely sealed and conformally coated. So you can technically submerge it. However, I would not recommend at the moment, until further testing is done, that the whole aircraft is submerged. But thanks to conformal coating and then our newest heat sinks, the whole aircraft is watertight. Obviously, it's not great for surveys if you get a bunch of water droplets on your lenses, and it's particularly not great for us if we get water droplets on any of our navigation equipment, because that does mess it. So we try to avoid water as much as we can.
Absolutely. Thank you. All right. Now, how long did it take for the survey and rehabilitation of the siphon?
Well, the original program was 32 weeks, but through the savings with utilising the drone, we were able to take 8 weeks off that. So it was a 26-week program overall.
Cool. Very good. Thank you. Okay. All right. When scanning with a drone, is there an operator to record the defects in the sewer, or are the defects recorded automatically by the instruments in the drone?
Depends on the question of if the defects are coded. So if we are wanting a full report out at the end, obviously as the drone is flying along, it is actively recording LiDAR and is actively recording video. But thanks to the speed of the drone, we have a bit of a curse on it goes that fast that if we had someone who was trying to type in the defects as the drone flew, they would be completely overwhelmed by, ingress 12 o'clock, connection 6 o'clock. It would be too fast for them to code. So what we're working on for that is a real-time machine vision that helps code as the drone flies. That is still a work in progress, and so the drone surveys need to be coded afterwards to get the chainage of where your defects may be. However, we are actively working on a machine vision that assists the operators so that the whole survey, including the coding of it, is done in one on-site and then ready to be shipped off to be looked at for remediation, or if it's okay.
All right. Thank you. Very interesting. Okay. What storage would I need to process and analyze the point cloud data collected from the drone survey to create accurate 3D models?
That is a fantastic question, and one that is actually pretty cool with the point clouds. So we record in 4K on our main forward-facing wide-angle camera. We now, in the newest designs, also have 2 additional 1080p cameras, which can go up to 4K on the sides as well, so you get a full 360 view. But if you can imagine a 12K video stream and the size that a 12K video stream would be, that's about 12 gigabytes a minute. Mm-hmm. So with 12 gigabytes a minute for a single survey that maybe is 20-25 minutes, you would not want the hard disks that would appear on someone who is processing these surveys' desk. So the handy thing with the point clouds is, although a single survey may be in the hundreds of gigabytes for the raw video data, the point cloud is actually in the 20 megabytes. So you can send it by a text message, which means that for processing, it contains all of the information that's necessary pertaining to the full flight. But the processing of that is incredibly simple, since it's very, very small and very lightweight to work with. Obviously, bigger point clouds are going to be a little bigger than 20 megabytes, but the actual storing of the information via point cloud is an incredibly efficient way to store that information.
Well, thank you. That's very interesting. Okay. A couple of questions on the same kind of topic here. In a 600 millimeter pipe, what is the maximum depth of flow that can be accommodated? Or does the flow have to be stopped with the line pumped out?
In a 600 millimeter, if you had something like a 10% flow, the problem that you would encounter when trying to do a drone survey is the amount of airflow that comes off the fans as the drone flies along will take that 10% flow and kick it up all around the pipe. So it will get, on top of your lenses. And there's not much we can do about that in terms of quality of survey. So if you're happy with the drone having, water splashing around as it surveys, then absolutely grand, 10%, 20% should be okay. Ideally, it's dry because then you get a proper survey of that.
Interesting.
You're also able to, there's the handy thing about the drone is in larger diameters, I mean, technically, you can fly to SI, which is the largest diameter of all, but there is no upper limit on how big a tunnel we can fly in. So as long as we have room for it, which with ample space above the water, we can go to very large diameters.
Cool. Very good. Thank you. We have time for just one more question here, and I got two that are remaining that are very similar here. I guess what is the speed of the drone, and can it be slowed down?
It can be slowed down. So we fly at about 0.75 to 1 meter per second, as we found in our testing that is the best compromise between the flight time that is achieved and the ability to see what is going on within the tunnel. It can be slowed down to hover and be still. But you have a time constraint with the drone survey of you have 25 minutes flight time. And since you have 25 minutes flight time, you have a 25-minute window to get as far as you can if you want a long distance survey. So generally at 1 meter per second, we find that we can get 600, 700 or 500, 600, don't want to overpromise, on a large diameter shaft or tunnel. Meters. So the drone can, if needs be, stop and have a look at things, so that you can really sort of analyze stuff and stop and have a look. But we found that 1 meter per second survey speed means that you're able to get the distance as well as get the quality of the survey.
Cool. All right. Well, thank you very much, ladies and gentlemen. I really appreciate the presentation here. This is quite fascinating. Getting a drone into such confined space is quite an achievement, such in the logistics and engineering of it. So thank you very much for your presentation. And I also like to thank you all to the CUIIC members here on our little slide here. We got quite a number of and diverse group of members. So thank you very much to everybody there. And I'd also like to thank all the people there, in our audience here to see this and to support CUIIC and the innovation that we're seeing on these webinars. So with that, again, thank you to our presenters. Thank you to everybody on the call and to Benjamin Media for being here. If you have any questions or anything else like that, feel free to reach out to CUIIC. If you have ideas for webinars that you'd like to present, do that as well, and we'll take a look at them. But with that, again, thank you, and hopefully everybody has a great day from now. Cheers.
Thank you. Thank you, Peter.